Hi everyone, this is Kiranmay from HNS department. Today in this session, we are going to discuss about Unit 5, Dielectric and Magnetic Properties, and the topic is the basic terms of magnetic properties. So we are going to learn about magnetic field intensity, magnetic field induction, magnetic dipole moment, magnetization, magnetic susceptibility, permeability, relative permeability, and some of the relations between the above terms. First of all, magnetic field intensity. This is defined as the at any point in the given magnetic field, the force experienced by unit north pole is nothing but magnetic field intensity. It is an analogous term for electric field intensity in dielectric materials, like force acting per unit area in a given electric field. That is per unit area, that will be given as electric field intensity, whereas here force acting per unit north pole will be given as magnetic field intensity, and the units for magnetic field intensity is ampere per meter. Then magnetic field induction. Magnetic field induction is nothing but it is the number of lines, the number of magnetic lines passing per unit area perpendicular to the material is called as magnetic field induction, which is given as phi by A, where phi represents the flux density, magnetic flux by magnetic flux by unit area, that is Weber per meter square or Tesla are the units for magnetic field induction. Then magnetic dipole. The arrangement of any two opposite poles separated by certain distance is called as magnetic dipole. Like in a bar magnet, you can observe north and south poles. These two poles got arranged and separated by certain distance. Then this arrangement is called as magnetic dipole. And for every bar magnet, there will be certain pole strength. Let that pole strength be small m, then multiplication of this pole strength with the distance between those two poles is called as magnetic dipole moment, which is defined as the product of magnetic pole strength with the length of the magnet is called as magnetic dipole moment, which is given by the units of ampere per meter square, ampere meter square. Then coming to magnetization, magnetic moment per unit volume of the substance is called as intensity of magnetization or magnetization. So it is represented with a letter I, and it is defined as the ratio of magnetic moment per unit volume. So the units are ampere per meter. Then magnetic susceptibility. Again, it is defined as the ratio of intensity of magnetization to magnetic field intensity, that is I by H. Since both the terms are having same units, there is no units for magnetic susceptibility. Both the denominator and numerator is having same units of ampere per meter. So cancelling each other, so there is no units for magnetic susceptibility. Coming to the permeability, this can be permeability is a property of the medium. The magnetic induction and magnetic field intensity H are rated as B is equal to mu naught H, where mu naught is called as permeability of free space. Then for a medium, B is equal to mu H, then where mu is equal to B by H is called as permeability. So it can be defined as magnetic field induction in the sample to the applied magnetic field intensity is called as permeability. Magnetic field induction in the sample to the applied magnetic field intensity is called as permeability, which is having a units of Henry per meter. Henry per meter. Then relative permeability, it is defined as the ratio of permeability of medium to permeability of free space, that is mu r is equal to mu by mu naught. Since both the denominator and numerator of same terms, there is no units for relative permeability. Coming to the relation between magnetic field induction, magnetic field intensity, and magnetization, we know that for a medium, B is equal to mu by H, and relative permeability mu r is equal to mu by mu naught. So from this, mu is equal to mu naught into mu r. Just substitute this in place of mu in this expression. So it can be written as mu naught mu r H. Now just add mu naught H and subtract it. You will get an expression mu naught H mu r minus 1 plus mu naught H, where H into mu r minus 1 is called as intensity of magnetization. I is equal to H into mu r minus 1. So mu naught is equal mu naught into I plus mu naught into H. If you take mu naught as common, mu naught of H plus I. This is the relation between magnetic flux density or magnetic field induction, magnetic field intensity, and magnetization. Coming to the relation between the relative permeability and susceptibility, as we know that mu r is equal to mu by mu naught, and B is equal to mu naught into H plus I. So from this you can write mu naught is equal to B by H plus I. So substituting the same in the formula, you are having one more formula. B is equal to mu H. From this, mu is equal to B by H. So using these two, mu naught and mu, just substituting them in the relative permeability formula, dB will cancel out. So H plus I by I, H by H is 1, I by H plus I by H. That is equal to 1 plus I by H is nothing but susceptibility. So 1 plus xi, mu r is equal to 1 plus xi, or xi is equal to mu r minus 1 is the relation between relative permeability to susceptibility. Then coming to the origin of magnetic moment, for that let us consider one atomic structure in which center nucleus is there, around that electrons are revolving. Let the radius of this atom be smaller. Okay, then every current carrying every atom is a minute current loop producing magnetic field, because here the electron is in motion around the nucleus. So the moment of electron produces current, hence this is a current loop with radius r. To calculate the current produced in that atom, we know that current is defined as charge per unit time. Here we are going to talk about the electron. So I is equal to charge of electron by time period of electron. That is, time period of electron can be given as, this is electron revolving orbit with the radius r. Then electron is revolving in this orbit. So the distance traveled by the electron is equal to 2 pi r. This is the distance traveled in a time of with a velocity of v. Then velocity v is equal to 2 pi r by distance traveled by time. Then time t is equal to 2 pi r by v. Just substituting the same in the expression, I is equal to ev by 2 pi r. From electromagnetic theory, the orbital magnetic dipole moment magnitude can be given as mu L is equal to I into A, where I is equal to EV by 2 pi r into pi r square. So pi cancel, r square r cancel, left over with EVR by 2. And we know that the relation between our angular momentum can be given as MVR. Now just divide mu L with L, you will get E by 2m, where VR and VR cancel out. This E by 2m is called as gyromagnetic ratio. So in the vector form, we can say that mu L is equal to gyrometric ratio into L, where minus indicates they are in opposite direction. And the units of magnetic dipole moment is ampere meter square or joule per Tesla. So from this, let us derive an expression for Bohr magneton, which can be derived using wave mechanics, where the parameter values of orbital quantum number is root over L into L plus 1 into H by 2 pi. So orbital magnetic moment is given by mu L is equal to L into E by 2m. Just replacing the same thing, you will get EH into 4 pi m. So that is this EH by 4 pi m is called as Bohr magneton. It is represented with a letter mu b. Therefore, mu b is equal to EH by 4 pi m, where E is charge of electron, that is 1.6 into 10 power minus 19 coulombs. H is Planck's constant, that is 6.6 into 10 power minus 34 joule second. M is mass of electron, that is 9.1 into 10 power minus 31 kg. So substituting all these values in the above formula, you will get a constant value for Bohr magneton, that is 9.28 into 10 power minus 24 ampere meter square. And the formula for uh, mu L, that is magnetic momentum, is equal to root over L into L plus 1 into mu B. Thank you.